Alright, welcome back. Today will be the second day of online notes for our last unit. Today we'll be looking at power series. This one will not have two parts like the first notes video I did, because this is a little bit of a meatier lesson and needs to be done all as one. Okay, so we've talked about infinite series before. These are a series of constants, is another name for it. And this is where we just have the variable of n that we're plugging in, where n goes to infinity. And so each term of the series becomes a constant. But if we have an infinite series whereas n is the variable we're plugging in, but we still have another variable such as x in it, this is what we call a power series. Now, a power series is what we call centered on whatever number is in there with x. So in this case, the power series is centered at 5, because that's what we get for sure as an equal value when we plug in 5 equals to x. Okay, so a power series is centered based on whatever is in the parentheses with x. So now we have an official definition for a power series. Power series, or if x is a variable, then an infinite series in the form of the sum from n equals 0 to infinity of a sub n times x minus c to the n equals a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, all the way on and on and on, is what we call a power series centered at c. Now this may start to look familiar because we kind of looked at some series centered at different things when we were looking at Taylor and Maclaurin series in the previous video. But this time we have an actual series. What we were looking at in the last video were just truncated polynomials for that. Okay, so a power series in x can be viewed as a function of x. So the function of x is equal to the sum, where the domain of f is the set of all x values for which the power series converges. Today, we're going to be looking at finding the domain of a power series. For every power series converges at its center, C. Now, there's a lot to say that we're going to be looking for what values does it converge. Does it converge only at C? Does there exist some real number R such that the series converges anytime it's less than R and diverges if it's greater than R? Or does it converge for all real numbers? We're going to be looking at all of these today to determine what actually happens with these series. The number R is what we call a radius of convergence of the power series. If the series converges only at C, then the radius of convergence is R equals 0. If the series converges for all x values, then the radius of convergence is infinity. The set of all x values is what we call the interval of convergence. So this R right here is radius of convergence. But when we set it up like this whole thing, let me undo that. When we set it up like this whole thing right here, where it's like an actual interval, this is what we call the interval of convergence. This is what we call the interval of convergence. Once again, mind my handwriting, it's not great. Try and pay attention to what I'm saying as I'm writing. It'll make it easier to see. So we have interval of convergence and radius of convergence. Those are the two big things we're going to be looking at today. We usually use the ratio test to find the interval of convergence. And we've already talked about the ratio test last unit. Hopefully, we've already talked about the ratio test last week. Hopefully, well, I guess it wouldn't be last week at this point. It would have been the week before spring break. Hopefully y'all remember what that is. So the ratio test says that the series will converge if this limit right here is less than 1. So we'll find whether the limit or what this limit is and determine what values of x we can use for that. Because we'll have an x inside of this little ratio there. Okay? So let's look at how that would work. So we're going to find the radius of convergence and the interval of convergence, and we have to check the endpoints. We'll talk about this part in a second, but it is something you're going to have to do in the end. So we're going to start by doing the ratio test. Now, if you remember from what we did last week or the week before spring break, you shouldn't have any problem doing this. You might work ahead, but I'm going to go ahead and just start with it. So limit as n approaches infinity, absolute value of -1 to the n plus 1 plus 1. This is where my handwriting is going to be really problematic here. Let me try and fix that. Let's see if I make it thinner, if that will help. Limit as n approaches infinity. I might just have to write big. Absolute value of -1 to the n plus 1 plus 1. So this is the plus 1 part of the an plus 1 part of this, times x minus 5 to the n plus 1 over n plus 1 times 2 to the n plus 1. Oh man, guys, this is really tough. All right, divided by, and then we do a sub n, so -1 to the n plus 1 times x minus 5 to the n over n2 to the n. Now this whole thing can be rewritten. We're going to rewrite this as the limit as n approaches infinity of -1 to the n plus 2 x minus 5 to the n plus 1 over n plus 1 times 2 to the n plus 1 times, and then we're going to multiply by the reciprocal of that part right there. So n 2 to the n over -1 to the n plus 1 times x minus 5 to the n. Absolute value. And this is what we're going to be simplifying. So let's look at what this simplifies. We have, and I'll use a different color so we can see what I'm talking about, -1 to the n plus 2 over -1 to the n plus 1. That just gives us -1. Okay. We have, let's see, let's pick a different color for the next part. Whoops. Sorry, guys. There we go. We have, if I select the marker, we have x minus 5 to the n plus 1 and x we'll move this over here. And x minus 5 to the n. This just leaves us with x minus 5. Then we have n plus 1 and n plus 1 will not cancel, so those are going to stay, but 2n over 2n plus 1, that should just give us over 2, and then we have n over n plus 1 still. And we're doing this with the limit as n approaches infinity. So make sure you have this marked. I'm going to clear the screen and just rewrite this part so it's all in the same color and all kind of together. Okay, so let's rewrite this. We have the limit as n approaches infinity, the absolute value of -1 times x minus 5 over, or times n over n plus 1 times 2. And now we need to find the limit of this as it goes to infinity. Now you would think this looks a little nasty because we have x and we have n and we have all these numbers, but some things really simplify out for us. This -1 is on the inside of the absolute value, so that's going to just go away. We could pull that out and make it go away. So we're left with the limit as n goes to infinity of just the absolute value of x minus 5 times n over 2 times n plus 1. Okay? And now we do our limit here. Now it looks pretty ugly, but what we could do, even if you can't see this as a horizontal asymptote, or you don't really want to take the derivative of it, what we can do is divide everything by n. So divide by n, and watch what happens here. So the limit as n goes to infinity of the absolute value of x minus 5, those n's cancel here, over 2 times n over n will just give us 2, plus 1 over n. And now as n goes to infinity, it's much easier to see. This just goes to 0. And we're just left with x minus 5, absolute value of x minus 5 over 2. All right, so now let's rewrite this. Okay, so let's rewrite this. This is now the absolute value of x minus 5 over the absolute value of 2. That's what we got when we did our ratio test. But if we go back to what we're looking for, we're looking for this to be less than 1. We want this to be less than 1. Now we found what that limit was. We now want to figure out what x values will make this less than 1. So now what we're going to do is we're going to treat it like an inequality. We're going to say, let's take this and let's set it less than 1. And then we'll solve it. So right now we have absolute value of x minus 5 is less than, well, the absolute value of 2 is just 2, and to get that away, we just multiply it, 2. So this tells us a few things. Well, it really only tells us one thing right now. It tells us what our radius of convergence is. So remember, we said earlier that the radius of convergence is going to be whatever this r is out here. That right there, that's going to be our radius of convergence. Well, specifically the r in here. So, to go back down to what we're asked for radius of convergence and interval of convergence. Oops. Okay, so radius of convergence and interval of convergence. We have the radius of convergence right now. That's this part right here. That's our radius. So r is equal to 2. Now we need to find the interval of convergence. To do that, we're going to change this into an actual interval. We're going to say -2 is less than absolute value of x minus 5, or not absolute value. There we go. Is less than x minus 5, which is less than 2. Or in other words, add this 5 to both sides and get 3 is less than x, which is less than 7. Now what we've just done is we've shown that as long as x is between 3 and 7, this series will converge. But if it's not between 3 and 7, that series won't converge, which is great. That's awesome. But what happens at 3 and 7? That's where this check your endpoints comes in. So this is where these problems can get a little bit longer. So what we're going to do, we're going to look at x equals 3, and x equals 7. And we're going to see what does the series do at these 2 points. So we have the sum of n equals 1 to infinity of negative 1 to the n plus 1 times, and then we'll plug in 3 for x. And that gives us negative 2 to the nth power over n times 2 to the nth power. And when we look at this, this can simplify pretty easily. We have the sum of n equals 1 to infinity of, well, we pull out this negative 1 to the n here, because that's just a negative 1 in there, and we have negative 1 to the n plus 1 times negative 1 to the n times 2 to the n over n times 2 to the n. And look at these two right there. Two little 2 to the n's that'll both cancel out. And we're left with the sum of n equals 1 to infinity. There we go. N equals 1 to infinity of negative 1 to the n plus 1 times n gives us n squared, or no, 2n, oops. Let me get my eraser back. Negative 1 to the 2n plus 1 over n. And now we start to see some interesting things. Because now, if we look at this, does this alternate anymore? And I would argue to say no, because the power is always going to be odd. So this just becomes the sum of n equals 1 to infinity of negative 1 over n. And we've actually talked about this series before. This was the harmonic series without the negative. So we could just pull that negative to the outside and say, what does this series do? And we should know that the harmonic series does not converge, so this diverges. Now, the thing with this is that because it diverged when we plugged in x equals 3, that means we are going to leave this as a strictly less than 3, or less than here. And now we're going to check what happens at x equals 7. So now we're going to clear out all this. And we're going to look what will happen when we do x equals 7 now. Okay, so let's do the same thing with x equals 7. So the sum, for n equals 1 to infinity, of negative 1 to the n plus 1 times 7 minus 5, that gives us 2 to the n, over n times 2 to the n. Those 2 to the n's will cancel. This time we don't have anything to pull out and multiply by that negative 1. So n equals 1 to infinity of negative 1 to the n plus 1 over 2 to the n. Or sorry, not 2 to the n. We just canceled out that 2 to the n, and we should be left with just n. This time, we have a harmonic series again, but it's alternating. So we can do the alternating series test. I'm not going to go through the whole process of writing it. You can look back at your notes from before spring break to see how we do that. But the alternating series test says this converges. So kind of the opposite of what we saw when we plugged in 3, because this one converges, we're going to put a equal sign there. So our final answer for this problem, after all this work, I know it's a lot, is going to be a radius of convergence of 2, that was the r we found earlier, and an interval of convergence at 3, which is less than x, which is less than or equal to 7. So we know that it converges within 2 of our center. so within 2 of 5. So our interval of convergence is going to be from 3 to 7, and we checked 7, and we know that it does converge when x equals 7, but it does not converge when x equals 3. And that would be the answer to that problem. I know it was a lot of work, and it's hard to see it sometimes, but from there, most of this is just your series test from before spring break. So try this one. I'll give you a chance to do it without me first, and then we'll look at it together. You can pause your video while you're working on it. Okay, welcome back. Let's look at this one. I'm going to go ahead and get some stuff written here, and I'm going to jump some steps just because it's hard to write. So I'm going to start by taking the limit as n approaches infinity, the absolute value of -1 to the n plus 1 times x to the 2n plus 3 over 2n plus 1, 2n plus 3, fix that, factorial. And then we're going to multiply this by 2n plus 1 factorial over -1 to the n times 2, or not 2, man, times x to the 2n plus 1. And this is what we're looking at this time. So, going to do a little bit more simplification, but a lot of it is going to be in the same vein as what we looked at yesterday, or with the last problem. So limit as n goes to infinity, absolute value, we're left with just another -1. The x to the 2n plus 3 over the x to the 2n plus 1 should just end up giving us x squared. And then the 2n plus 1 over 2n plus 3 factorial, both of them being factorial, those will actually cancel out and we'll just end up with 2n plus 3 times 2n plus 2 on the bottom. Now look what happens whenever we do this. Limit as n goes to infinity of the absolute value of x squared over 2n plus 3 times 2n plus 2. And when n goes to infinity, this whole thing is going to go to 0. Which, if we look back up, that is always going to be less than 1. Because remember, we're looking for the radius of convergence to be less than 1. So, if this is equal to 0, and this is, I said radius of convergence, the ratio test to be less than 1, and this is always less than 1, then that tells us that this whole series will always converge. That will always converge. Now, what that tells us, if we look back at what we saw earlier, and now let me clear the screen. There we go. So, if the series converges for all x, then we say the radius of convergence is infinity. So let's go look. We said that it converged for all x. So that means when we're answering our question, we say that the radius of convergence, and I shouldn't be using ROC because we use ROC for rate of change. We'll just use R, is infinity, and the interval of convergence is when x is less than infinity or greater than negative infinity. Much easier problem than the last one we did. Okay? Let's look at the next one. Okay? Last one we're going to look at together. It was a much shorter video than last time. Okay? So for this one, I want to let y'all go ahead and try it on your own first, and then we'll look at it together. You can pause the video while you're working on it. Alright, welcome back. So here we go. We're doing the limit as n approaches infinity, absolute value of n plus 1 factorial times x to the n, x minus 3 to the n plus 1. This time, instead of multiplying by the reciprocal, since it's all one thing and not a fraction, we're just going to divide by n factorial times x minus 3 to the n. This time, we'll look at the limit as n goes to infinity when we simplify, and we're left with the x minus 3 to the n plus 1 over x minus 3 to the n. That just gives us x minus 3. And then the n plus 1 factorial over n factorial just gives us n plus 1. This time when we look at this, as n approaches infinity, this goes to infinity, which is greater than 1. So since this is always greater than 1, that means there's no other x we can plug in there to make it converge. Now, we do know that it definitely has to converge at 3. Okay, we will have to converge at 3 because that's what's called our center. That's where it's centered at. That means they have the same value at that point. But because we get infinity here, that means it will only converge at 3. So when we go back and look up top, we see that if the series only converges at C, then the radius of convergence is r equals 0. Now, some of y'all might be asking, why don't we say this diverges? Because there's a reason power series have a center of convergence. For a power series, it will always, always, always do one of these 3 things that we talked about earlier. Nothing else. It can either only converge at C, it will either have a interval convergence, or it will converge for all real numbers. Well, it doesn't converge for all real numbers. It doesn't have an interval of convergence, so the only place it'll converge is at C. So, let's look at how we'll write this answer. Because it only converged at C, our radius is going to equal 0, and we will not have an interval of convergence for this one. There's nothing to check. If you were going to do it, you'd say x minus 3 is less than 0, and then, or absolute value of x minus 3 is less than 0, and so that says 0 is less than x minus 3, which is less than 0, 3 is less than x minus 3, which is less than 3, or sorry, 3 is less than x, which is less than 3. Well, this just means x has to be 3. That's the only thing that could happen here. And so we wouldn't have an interval of convergence. We'd only have a radius of convergence. Right, that's everything for this lesson. You'll have a worksheet posted in Learning with this same information. You can check that after this. And so you'll have the note sheet, the worksheet, and within the next couple days, you'll be seeing posts on It's Learning about it. But I will also be assigning things through College Board. Make sure you can access your AP Classroom account on College Board. If you cannot, please let me know. I'll be sending this out in email as well. You probably would have already gotten it by the time you saw this video, but make sure you're checking. All right? Y'all have a great day.